Here is your trig example. As promised, this fits number 6 on the online homework that some of you may have struggled with. So I'm choosing to do f of theta equals 2 cosine theta minus cosine 2 theta. Now on the trig examples, when we find maxes and mins in concavity, because trigonometric functions are sinusoidal, they have an infinite number of maxes and mins and an infinite number of inflection points. So we're going to limit it from just 0 to 2 pi, where 0 is not included and 2 pi is. Now under here, I've kind of written 2 pi as a decimal, because on the online homework, they want all the answers rounded to 2 decimal places. So 2 pi, okay, 2 times 3.14 is 6.28. So we're looking for angles between 0 and 6.28 in radians. So in order to start this, we're going to do the increasing, decreasing test and the first derivative test first. So let's go ahead and take the first derivative. The derivative 2 cosine theta, this is just a constant times cosine, so we're going to get the constant 2 times the derivative cosine. And then over here, cosine 2 theta, this requires a chain rule because the derivative cosine, or because 2 theta is inside a cosine. So I'm going to go ahead and outline the chain rule here. The outside function is going to be cosine x, and the inside function is going to be 2 theta. So then the derivative of cosine is negative sine x, and the derivative of 2 theta is 2. So if I plug b into a prime and multiply times b prime, I get negative sine of 2 theta times 2, which can be simplified to negative 2 sine 2 theta. All right, so that's going to be the derivative of the second term here. So the first term then, let's go ahead and fill out what the derivative is. 2 times the derivative of cosine. So 2 times negative sine is negative 2 sine theta. And then we're going to get a minus a negative 2 sine 2 theta. So that's going to change that to a plus. So I get plus 2 sine 2 theta. Here's the derivative. Now, the critical number where the derivative equals 0, and there's critical numbers where the derivative does not exist. But sinusoidal functions exist everywhere. So we don't have to worry about where the derivative does not exist. We just have to worry about where the derivative equals 0. So I'm going to set this equation equal to 0. Now if you notice, inside the sine function, one of the arguments is theta and one of the arguments is 2 theta. This is a problem because we can't, they're different, okay? They're different terms. So I would like to get everything as single angles. So I am going to use a trig substitution for this double angle here, right? Sine of 2 theta has a formula. It's one of those ones, okay? You can look it up. It's in the cover of your book. Maybe you have it memorized. Maybe you have a cheat sheet with them all written down. You might want to grab those out. Okay, so sine of 2 theta is 2 sine theta cosine theta. So I'm going to make this replacement here. Right? So now I have the equation negative 2 sine theta plus 4 sine theta cosine theta equals 0. Because we had a 2 here, and then times the 2 sine theta cosine theta becomes 4. Right? This is good, okay? Because now we have like terms that we can factor out. Everything has a single angle in there, okay? So in order to solve this, I want to factor it. We could take a sine theta out of both terms. We could also take a negative 2, so that's what I'm going to factor out. So if I factor out negative 2 sine theta, I'm left with 1 minus 2 cosine theta. And then what I want to do is I want to set both of those factors equal to 0. So I get negative 2 sine theta equals 0, and I get 1 minus 2 cosine theta equals 0. All right, so if I solve these, I'm going to divide by negative 2. So I get sine theta equals 0. Sine of what angle is 0? That's how you solve this one. So I am going to kind of look at a unit circle. And instead of putting pies in here, I'm going to put their decimal representation. So 0 is 0, pi over 2 is 1.57, pi is 3.14, 3 pi over 2 is 4.71, I believe. And then 2 pi is 6.28. So we know them with pies in them, but sometimes this homework problem is going to ask for 2 decimal places. So I just want you to recognize the real number values of these angles. So we're looking for where the sine, what angles where sine is 0. So remember, sine is the y-coordinate. So x, comma, 0. Where is y equal to 0 on the unit circle? Where it's here on the x-axis, right? So we get angles 0, pi, 2 pi, okay, all the whole pies. And so I am going to write the critical numbers that are in our restricted domain here. So I'm not going to include 0, right? The first critical number is going to be 3.14, and then the next time it hits 0 is 6.28, and 6.28 is included in our restricted domain there. So I get 2 critical numbers for this equation. All right, so then if I go to the other equation, 1 minus 2 cosine theta equals 0, go ahead and solve it for cosine. So we're going to subtract 1 from both sides. Divide by negative 2. I get cosine theta equals 1/2. All right, so you may remember, that this is pi over 3, okay? But you're going to want the decimal for pi over 3, so you can, calculate that out. Or you can use your calculator here, actually, right? So if I were to cosine inverse both sides here, and I do cosine inverse of 1/2, the calculator is only going to give me one solution, but there are indeed 2, and I'm going to try and explain to you how to find the second one. So first, though, I want to make sure that my calculator is in radian mode, and it is not. So I'm going to change this calculator to radian mode. And then I'm going to insert cosine inverse of 1/2. I get 1.04719. So if I round that to 2 decimal places, we're looking at 1.05. That's the radian measure of the angle. So if I were to look on the unit circle, right, this is a radian measure of 0. This one is 1.57. So let me go ahead and write the answer here, 1.05. Getting a radian measure of 1.05, that angle is going to fall in quadrant 1. Okay, and it's going to be about, I'm just going to eyeball it here. This is where the angle is 1.05. Okay. Now there are 2 answers, because what other angle is going to give you a cosine of 1/2? Remember the x value is the cosine, so we're looking for 1/2 comma y, right? So the x value is 1/2 here. So we have 1 in quadrant 4, and we have another point where we get 1/2 comma y in quadrant 4. So how do we calculate that? Well, the reference angle is still 1.05. Okay, we can go 1.5 in the counterclockwise direction, or we can go 1.05 in the clockwise direction. Instead of writing this as minus 1.05, we want to rotate and make sure that angle's between 0 and 6.28, right? Because this is 6.28. So to get all the way around to this one, we're going to do 6.28 minus 1.05. So let's go ahead and do that. 6.28 minus 1.05. That gives us a measure of 5.23. Okay, so these are our critical numbers in radians, okay, or in real numbers, without the pies, all right, because they want everything rounded to 2 decimal places. So we could have done, you know, pi over 3 and 5 pi over 3. If I were to do 5 pi over 3, I just want to show you, it would equal 5.23. Okay, 1.05 is really just pi over 3. So we're getting the same, you know, radian measures here. We're just converting them to decimals. All right, so on my number line, I have 4 critical numbers in this restricted domain 0 to 2 pi. So I am going to go ahead and do a number line analysis. All right, I'm going to start at 0, and then we'll get to 1.05. Then we'll get to 3.14, then 5.23, and then 6.28. So my critical, or my intervals, I'm not going to go before 0. I'm going to kind of start it here and end it here. So I have 1, 2, 3, 4 intervals, right, to test. And so I think what I'm going to do here, instead of, you know, putting my factors down, I'm just going to plug the derivative as a whole into my y equals and go ahead and pick test points. But let's go ahead and pick our test points. Right? A test point between 0 and 1.05. Let's go ahead and pick 1. Let's make it easy. A test point between 1.05 and 3.14. I'm going to use 2. A test point between 3.14 and 5.23. I'm going to pick 4. And then our last test point between 5.23 and 6.28, I'll go ahead and pick 6, just so I can have some nice whole numbers. All right, so now I'm going to go to my calculator. I want to plug the derivative into this function. Okay, which one do I want to plug in? We can plug in, you know, this derivative with the double angle, or we could plug in this one. Or we could plug in the factored form. It doesn't really matter. Maybe I'll go back up to the beginning here. No, let's do this one. I'm going to do negative 2 sine x plus 4 sine x cos x. Negative 2 sine x plus 4 sine x cos x. Okay. So if I were to plug those critical numbers in there, I should be getting 0. But if I plug the test points in there, okay, I'm either going to get a positive value or a negative value, and that's what I'm interested in. So I am going to go to the table now. All right, if I plug 0 in there, I just want to show you we will get 0. Okay, but I want to plug a test point 1. And when I plug 1 in there, I'm getting a positive 0.13. So I'm going to put plus here. If I plug in 2, I get a negative 3.32, so I'm going to put a minus here. If I plug in 4, I'm going to get a positive 3.49. If I plug in 6, I get a negative 0.54. So it is kind of changing positive to negative, positive to negative. So if the derivative is positive, our function is increasing. If the derivative is negative, our function is decreasing. So I have increasing from 0 to 1.05, union 3.14 to 5.23, decreasing from 1.05 to 3.14, union 5.23 to 6.28. So then we can calculate maxes and mins. We're not going to include the endpoints because we don't have any data passed here. So we're going to have a increasing to decreasing here. So 1.05 is a max. We have a decreasing to increasing here. So 3.14 is a min. And then positive to negative, increasing to decreasing, 5.23 is another max. And we don't know what 6.28 is. All right, so here is the first derivative test and the increasing, decreasing test. And my 15 minutes is up, so I'll do the second derivative on the next video.